Welcome to this short teaser for my C++ online workshop, C++ Software Design. In the short teaser, I want to convince you that it's definitely worth joining. And of course, I want to give you an idea what to expect from this one-day workshop. So first, who am I? Well, my name is Klaus Iglberger. And in the workshop itself, it's perfectly okay if you would stick to the first name. I've been doing C++ for about 20 years now. And I've been working as a C++ trainer/consultant since approximately 2016. I'm also the author of the book C++ Software Design, which is the basis for this one-day workshop. And then I'm also one of the co-organizers of the Munich C++ user group, and I do various things at various C++ conferences. So in other words, a lot of C++ for me. But now, what can you expect from this one-day workshop? So we're going to talk about software design. And in order to give you an idea what I mean by that, let's take a look at a short motivational example. So now, of course, at this point, you're expecting an amazing example, an exciting example with many, many facets. No, I don't have this example. So what we're now doing is something very simple, very basic. We are going to draw a couple of shapes. And okay, I know this is probably the most boring example that I could have chosen, but it's a simple example. And therefore, I believe we can entirely focus on the design of the coming piece of code. So we are going to draw a couple of shapes. And in order to do so, we're first defining a shape type enumeration. So this shape type enumeration lists all the shapes that we're going to have. And yes, for the short demo, we'll just have circles and squares, but please imagine that there are many, many other shapes, triangles, rectangles, ellipses, you name it. So possibly we have 10 different kinds of shapes. But then we also have a shape base class. So this base class is not particularly difficult. It has an explicit constructor. It has a virtual destructor, and it has a getTypeMember function. The getTypeMember function gives you a copy of this shape type enumeration. So the shape class stores which kind of shape it is. Circle, square, rectangle, could be any shape. Now, this base class is used for various different kinds of shapes. For instance, the circle class. So circle publicly inherits from shape, and of course, first defines everything that a circle needs. So a radius, perhaps a center point, perhaps a rotation, all kinds of stuff that circles need. Probably the most interesting line of code, though, is this one. The circle initializes its base class. Well, it's a circle, so it initializes itself as a circle. Makes sense, right? So, but then, of course, we have various other operations on a circle. So we can translate a circle, meaning move the center point by a certain offset. We can rotate a circle. Okay, and that sounds boring, rotating a circle. But we can also draw the circle. And now imagine that there's a texture on the circle, and then, of course, you can see it rotating. No, pretty exciting. So then we also have a square class, which I have to admit is pretty much the same thing, except that it's edgy and not round. So also the square defines all kinds of things. So a square probably is a side length, potentially a center point too. But of course, it now initializes its base class to square, right? It's a square after all. And then also a square can be translated, rotated, and drawn. So now I can draw the different kinds of shapes, but I do not just want to draw a single shape. I want to draw many shapes. And hence, I now have a draw all shapes function, which draws an entire vector of shapes. So vector of shapes means vector of base pointers, so a vector of unique pointers of shape, which is quite a mouthful, but that's not exactly what we have to traverse. So we run over all those shapes one by one. And quite honestly, we don't know exactly what to do because it's all base pointers. And so we actually have to ask nicely, So what are you? Circle or square? Well, if the answer is circle, okay, then we know what to do. We literally get the raw pointer, convert it into a circle pointer by means of a static cast, and draw the circle. Done. Circle is drawn. And if it's a square, of course, we know what to do also. We get the pointer, convert it to a square pointer, and draw the square. Yes. And this works. Guarantee. Which you can kind of prove in the main function. We first abbreviate this long type vector of unique pointers of shape into shapes, and then start to fill these vectors one by one. So we might create a circle with a radius of 2.0, might create a square with a side length of 1.5, and then we might create a second circle. So we fill this vector up before we draw all the shapes. And this, hooray, this works. You can now imagine 3 beautifully drawn shapes on the screen. Great. Yes. Now, of course, I know. This is the point where you start to shake that, say, that is a weird first example. How is this going to motivate me to change, to join this workshop? I've never been to any workshop. I've never given any training class where people like this example. No, nobody likes that. Everybody feels that it's kind of old. But I believe there is another reason why people don't like this. A much more basic reason, a very important reason. Yes, you're not thinking about what would happen if you would add another kind of shape. Yes. So imagine that we're now adding a rectangle. So any other kind of shape. So this line of code looks innocent. It looks basic. It looks simple. Anybody can do it. But unfortunately, this line is quite problematic already. First, because not everybody can do it. No, this line can only be added by somebody who has access to this enumeration. So imagine this is in a library. Would you like to change code in a library? No. No, you want to be able to add code, to extend the code by not modifying the existing code. But then this line results in an ABI break too. So that means that the compiler might choose, and note that I said might, not will, might choose a different representation of this shape type. Yes, so it might be that it now chooses a bigger data type. Or you have added the rectangle not at the end, but somewhere in the middle, and changed all the numbers. Which now fortunately means that all the code, and really all the code that deals with the shape type has to recompile. And so first and foremost, this means that the circle class has to recompile. That doesn't feel right. This feels wrong. Adding a rectangle should not have any influence on circles or squares. They should be totally independent. That really feels wrong. But then there's more. Yes, of course, I now also have to change the draw all shapes function. Of course, we have to deal with rectangles as well. And yes, of course, this feels like duplication. Yeah, this is one of these situations where people are tempted to use copy and paste. But there's a much bigger problem here. So yes, this example is probably not even 200 lines of code. It's simple, it's short, and nobody would care about this tiny example in a real world. But let's imagine that you would use this style of programming in a real code base. Not a small one, a big one. This is what matters. So we have now at least 1 million lines of code, at least, potentially many more. Now, in a real code base, with this style of programming, how many switch statements would I have to change? Would I have to adapt to add rectangles? 50? Perhaps 100? Oh, perhaps even 200? Whoa. And now you might finally realize why you dislike this code so much. This would be an enormous endeavor to extend, an enormous endeavor indeed. You would have to change across the entire code base, and you would have to find all of these places first. Imagine the pull request, 200 touched files. Oh, nobody wants to do that. So this style of programming is problematic. It really is. And this is not just my personal opinion. Decades ago, Scott Myers has written about this in his book, More Effective C++. This kind of type-based programming has a long history in C. And one of the things that we know about it is that it yields programs that are essentially unmaintainable. Unmaintainable. That's exactly the word that nobody wants to hear. That's exactly the thing that is considered to be so problematic. And so, what we really have to talk about when we talk about software design is that things change. Code changes. And sometimes even the things that we would expect to never change. So, which is nicely expressed by Pete Goodliff in Becoming a Better Programmer. Nothing is set in stone. No code is sacred. Everything changes. Code changes. It really does. Once again, even the things that we expect do not change. So, but this alone is just a fact. That's not a big problem. No, the problem is a different one. Because one thing depends on another thing. And so the core problem of adaptable software, the core problem that we encounter when we change software are the dependencies. Things depend on each other. Some piece of code depends on another piece of code. And if this other piece of code changes, well, your code might change as well. And this can create this avalanche of changes running over the entire code base. So dependencies, they make changes and modifications so much more difficult. Sometimes so difficult that nobody wants to change it anymore. Dependencies also impede the testability of software, where tests are the backbone, the thing that tells you that everything is all right, the thing that raises your confidence. With many dependencies, you might not be able to test properly. Then dependencies obstruct modularity, reusability. They may obstruct properly structuring the software so that you can reuse code. I would also consider this a big problem. And finally, dependencies increase build times quite a lot. So now you might frown and argue, build times? That's not as important as the other 3 points, is it? I think it is. So if you change this enumeration, if suddenly everything recompiles, and you have to wait for 15 minutes, perhaps an hour in a really quick code base, then techniques like test-driven development, for instance, are completely out of range. And the things that, again, raise our confidence, the techniques that have proven to work well, are not possible anymore. And so dependencies, I believe, are a really, really big issue. And again, that's not just my opinion. That's the opinion of many other people. Like, for instance, Kent Beck, the inventor of test-driven development, who in his book says that dependency is the key problem in software development at all scales. So on an implementation level, on a design level, on an architecture level, dependency is the key problem. And perhaps in another set of words, Ian Cooper said that coupling is a worse enemy for you than dry. Coupling is what kills all software. So this is not exactly what we're going to do in this training class. We're going to talk about dependencies. We're going to talk about coupling, and we're going to try to reduce coupling. So the primary guideline that I will talk about in this one-day workshop is that when we design software, modules, classes, functions, which is to say pretty much on all levels, we should try to minimize coupling between software components. So try to. Try to means that it might be difficult. And it is really difficult. I would argue that this is exactly the most difficult thing in software that we have to deal with. And therefore, in this workshop, we're going to talk about techniques, how to deal with dependencies, how to manage dependencies. So in the workshop, we will also talk about some motivation. And we're going to see that, of course, this procedural style is not going to work well, but that also naive object-oriented programming is not going to work well. We need more. We need some idea, a real idea how to manage design. So then we're going to talk about software architecture and software design as a primer. Not for long because it's just a one-day workshop, but you will get the point, what we try to achieve. And then we're going to start to talk about solutions, ways to manage dependencies. So we're going to talk about the visitor design pattern. This is a gang of four pattern. So a classic, 30-year-old one design pattern. But we're not going to just talk about how it was done 31 years ago. We're going to talk about how we do this today. And you realize that C++ has tremendously improved, that today's solution is so much better, so much simpler, faster, and just so much clearer and more understandable, so more maintainable. Then we're going to talk about the strategy design pattern. Again, in the old way of doing things, but also in the new way, the modern way. And again, the modern way is so much better, so much faster, so much clearer and more understandable. The reason why this modern C++ is so much better, so much clearer, is because we're investing more into values. And so we'll have a little interlude and talk about value semantics for a bit. Before then, afterwards, we talk about a couple of solutions that I personally feel are really, really amazing. So, namely, external polymorphism, and then finally, type erasure. This type erasure is something that we do a lot in modern C++ for many, many good reasons. First, for a design reason, but second, also for a performance reason. And as an addition, we'll also throw in the prototype design pattern, which we'll actually might need in order to do copy operations in this type erasure setting. So overall, you will have a pretty good picture about how to design software today in modern C++. And you will have an appreciation of why it is so important to deal with this in the first place. So I very much hope that you will join me on April 13th. And I'm really eager to talk about this software design.